Now a sequence, it may be a convergent sequence, and if a sequence does not converge, then we say the sequence is a divergent sequence. So any sequence which does not have a limit or does not converge is said to be divergent. Now what are the conditions that a sequence is divergent? If a sequence, it diverges to plus infinite or minus infinite or more than one limit points, or it have oscillating values, then the sequence is said to be a divergent sequence. Now there are some theorems on divergence, and the first one is if the sequences fn and phi n, they diverge to infinity, then both fn plus phi n and fn into phi n diverge to infinity as well. Second theorem is if fn diverges to infinity and phi n is bounded, then fn plus phi n, it also diverges to infinity. Now third theorem is if fn diverges to infinity and phi n is a convergent sequence, then fn plus phi n, it also diverges to infinity. And the fourth theorem is if we have two sequences fn and phi n such that fn is greater than or equal to phi n and phi n diverges to infinity, then this sequence fn, it also diverges to infinity. And in the same way, if fn is less than phi n and if phi n diverges to minus infinity, then fn also diverges to minus infinity. Let us take up an example. Say for example, let x1 be 1 and xn plus 1 be xn plus 1 upon xn square. Now the first part is show that xn plus 1 cube is greater than xn cube plus 3. Now what we'll do is we'll take cube, both sides we can write xn plus 1 cube and it'll be equal to xn plus 1 upon xn square whole cube. Now it'll be xn cube plus 1 upon xn to the power 6 plus 3, 1 upon xn cube and plus 3. Now since x1 is equal to 1 and xn plus 1 is given by this recursive relation, we can say any xn is greater than 0. And if xn is greater than 0, then xn cube plus 1 upon xn to the power 6 plus 3 upon xn cube plus 3 will always be greater than xn cube plus 3. So that's our first part of the result, which is xn plus 1 cube, it is greater than xn cube plus 3. Now we'll come to this second part, and the second part is we need to prove that xn is greater than or equal to cube root of 3n minus 2. Now for the second part, we need to prove that xn is greater than or equal to cube root of 3n minus 2. Now we'll prove this result using mathematical induction. So we'll prove this result when n is 1. So we can write x1, it is greater than or equal to cube root of 3n minus 2. And here the value of n is 1. So it will be greater than or equal to 1. And the question it says x1 equals to 1. That means p1 is true. Now we'll let pk be true. Now if pk is true, then we can write xk and it will be greater than or equal to cube root of 3k minus 2. Now we have to prove this result for pk plus 1. Now for pk plus 1, we need to write xk plus 1. Now we know that xk plus 1 cube, it will be greater than xk cube plus 3, and this xk, it is greater than or equal to this 3k minus 2. So we can write this as 3k minus 2 plus 3. So from here we can write xk plus 1, it will be greater than or equal to 3k plus 1 minus 2 whole cube root. That means pk plus 1 is true. So from induction we can say that xn will always be greater than or equal to cube root of 3n minus 2. Now this third part is show that xn diverges. Now in part B, we have already shown that xn is greater than or equal to cube root of 3n minus 2. Now, if we take this limit n tends to infinite, cube root of 3n minus 2, we know that this limit, it diverges to plus infinite. And since xn is greater than fn and fn, it diverges, from here we can say that this xn also diverges to infinity using theorems on divergence. So from here we can say that the sequence xn diverges. Let fn and gn be two sequences such that fn plus gn and fn into gn converge. Show by an example that the sequence fn and gn may fail to converge. Now let us take an example where fn is minus 1 to the power n and gn is minus 1 to the power n plus 1. Now we look at fn plus gn. fn plus gn, in this case it will be simply 0, and this constant sequence, it always converges to 0. Whereas both fn and gn, they have oscillating values at infinity, plus 1 and minus 1, and both these sequences, they do not converge. So it is an example in which fn plus gn, it converges, but fn and gn, they both fail to converge. Now considering the same example, if we take fn into gn will be minus 1 to the power 2n plus 1, and which is simply minus 1. Now again it is a constant sequence. Now this constant sequence again, it converges to minus 1, whereas both fn and gn, they fail to converge. So this is one such example.